Okay, now let's talk about flying. What affects the energy density of this? Are there ways to make it better? Now, so far when we've talked about any form of transport, we've talked about the kinetic energy to accelerate, the potential energy to climb. In the case of aircraft, there is no friction or no rolling resistance. However, for flight, there is a new form of energy we've not needed to consider before, which is the energy to stay in the air. Bear in mind, if you have a helicopter or a plane and it runs out of fuel, it will generally fall out of the air. Slower or faster, but it will not stay up. So you clearly need some form of energy just to stay in the air, quite irrespective of moving forward. So that's what we're going to talk about in this video. So let's imagine you have some aircraft, a helicopter or a plane or a drone or something. It has a mass. As it's floating in the air, it's got a mass that's pulling it downwards with the force mg. To stop it from falling out of the sky, there has to be some equal and opposite force pushing upwards, also of mg. Now for a rocket, the way that works is you fire stuff out the bottom and the recoil from that holds you up. And it's something similar for aircraft. But in this case, rather than pushing the rocket fuel down, they take air from around them and push them down. So for a helicopter, this is straightforward. The blades rotate and push air down, and the recoil from that holds the helicopter up. For an airplane, it's a bit more complicated. The air flows past the wings and is diverted into a downward speed, and that's what keeps things up. Now note that you often see explanations for how a plane works along the lines of Bernoulli's effect means the pressure on the top of the wing are less. That's actually not really accurate. And even if it was accurate, it doesn't really explain the underlying physics. Basically, you have to push something down, and that something is air, and you get air that flows near the wings is deflected into a downwards angle by things like the Bernoulli effect, and that's what keeps it up in the air. So let's look at the maths of this. Let's imagine we're pushing a certain amount of mass m dot down per second at some speed v. So v is not the speed at which the aircraft is moving forward, it's the speed at which the air is being pushed downwards by the rotating helicopter blade or the deflection from the wing or whatever. Okay, so there's a definition: force equals rate of change of momentum, which tells us that force equals the momentum change of all the mass being pushed down, which is the mass per second times the velocity. So momentum is mass times velocity, so the rate of change of momentum, how much momentum you're imparting to the air, is the mass per second times the velocity. You can also, if you don't know this equation about force's rate of change of momentum, you can use F equals ma. You're putting a mass, you have to accelerate it up to some speed v per second, so acceleration is v over t, so force is mass times v over t, which is mass over time times the velocity, m dot v. But this gives you a choice. Because the force is equal to the mass per second times the velocity, to stay in the air, you could either push a very large mass down at a low velocity, or push a small mass down at a high velocity, or any combination of the two, as long as the product of them multiplying together gives you the weight of your aircraft. Okay, so that's how you stay in the air. How much power do you need to make this work? Well, you're pushing air down, so you need to give that air kinetic energy. So you need power. Energy per second is half mv squared, so power is m dot v, half m dot v squared. So that's mass per second, that's what the dot on top means, v squared. So the power you need depends on v squared, but the force only depends on v. So if you factor this, the force is normally fixed, the force is whatever you need to keep your particular aircraft in the air. So let's plug that into here. We find that the total power is a half times the force you need times the v. So pushing a small mass down at a high speed is going to take more energy than a large mass at a low speed. High mass or low mass makes no difference in terms of the force. You just replace it with the velocity, but because power depends on velocity squared, it really penalizes high velocities. So what you're better off is having a very large m dot and a very small v. Still gives you the force you need to stay in the air, but it reduces this, because it depends on m dot v squared. And you can see that here, to keep a given force, to keep a given mass in the air, the power needed is going to go up with the velocity. Okay, so this actually affects what you see in the air. If you go outdoors and see what's flying over, you will typically see a lot of planes, a few helicopters, and almost no jetpacks. The reason is that an aircraft deflects a large mass of air downwards at a relatively slow speed, so they're quite energy efficient. Helicopter blows a smaller amount of mass down faster, so they're less energy efficient, and a jetpack blows a very small amount of air down really fast, which means they're extremely inefficient, which is why you don't see jetpacks all over the place. Now, the fundamental problem with pushing things down is you're pushing air down, and air's density is quite low. Wouldn't it be nice to push something more dense down? Well, you can do that. This is pushing water down. You've got a jet ski at the bottom, which pumps the water up and pushes it down. Because water has a density of 1,000 kilograms per cubic meter, that actually means you can be very efficient. So that's one way jetpacks do work. You push water down. But of course it only works when you're close to the water. It's not really practical for most purposes. It's a lot of fun, it looks like. But anyway, if we're restricted to pushing air down, this will be much easier if you're on a planet with denser atmosphere. But we're on Earth, we have to deal with that pathetic little 1.2 kilograms per cubic meter. Let's look at the numbers. So here we get the, let's look at a particular specific example, which is a UH-60M Black Hawk helicopter. It's a mass of up to 10 tons when it's fully loaded, power of 2.8 megawatts, and speed of about 280 kilometers per hour. So how fast do we have to push the air down to keep this in the air? Okay, so it's got rotor blades that are 8 meters in radius. So that means the area swept out by the rotor blades is pi r squared, which is about 200 square meters. So you're pushing 200 square meters of air down at velocity v. So the total mass you push down is equal to the area times the velocity times the density of air. So that's m dot. M dot times v must equal the mass, which is 10 tons, 10 to the 4 kilograms times g, which is about 10, so about 10 to the 5 newtons. So force equals m dot v equals a rho v squared equals mg. Rearranging that, we find that the velocity at which it needs to push the air down is equal to root mg over a rho, which turns out to come to about 20 meters per second, which is about 70 kilometers per hour. So that's a pretty strong wind, and indeed that's what you see from pictures of helicopters here. It's blowing people around underneath them. This means, if you plug that velocity into this equation, you're pushing about 5 tons of air down every second to keep your 10-ton helicopter in the air. And the power, half FV, is about 1 megawatt just to stay in the air. These aircraft actually have 2 engines, which between them, so 1.4 megawatts each, so 2.8 between them. Most helicopters often have double engines, so that if one fails, the other one can still keep it in the air. So it's got more power than it needs just to stay in the air, and it needs that because it needs to be able to actually move or climb. This actually is why we don't really have flying cars. We have plenty of flying things called helicopters or aircraft, but a flying car would be something that could drive down a road and then take off, maybe stay in your garage, something that everybody could own to get around. And that means it has to be fairly small. It has to be able to fit on a road or in a garage or a house. That means that you can't have, for example, 16-meter diameter helicopter blades, because that definitely won't fit on a road. It would be chopping up all the other cars near you, chop down your trees in your house. It has to be quite small, which means you're going to need a small area. So many ideas for flying cars have like fans. Because your area is small, you're going to have to push the air harder with a larger velocity to keep in the air. So we've seen that if you have a helicopter with a very large area, 8 meters radius, you need a megawatt of power. So if you're going to have something comparable with a smaller area, so it's actually a flying car, you're going to need several megawatts of power. Several megawatts means you're going to need hundreds of kilograms of battery to stay in the air for just 1 minute, let alone for 20, 30 minutes or whatever you need to drive somewhere. So unless you can make your flying car very lightweight, this means that battery-powered flying cars are really pretty prohibitive. The energy consumption is just so enormous. You do have battery-powered flying devices like drones, and the way they get away with it is by being really lightweight. But whether you actually build a light enough weight car, it's got to clearly weigh a lot less than the 7 tons of a Black Hawk helicopter, while still having all the battery power you need and enough safety features and fitting the people in, that's a formidable challenge.